start by welcoming back everyone to the final session of our Transitioning from Pesticides to Biopesticides webinar series. I am Claudia Costa, the Academy Director of Food for Sustainability, which on behalf of the GROW Consortium brings these webinars to you. And as you know, these webinars are an initiative from GROW, a project from EIT Food, the European Institute of Innovation and Technology, which is a food-focused body working to transform our food systems to become healthier, more sustainable, and more trusted. And today we'll be tackling a critical emerging concern, the presence of PFAS, the forever chemicals, particularly TFA, in our environment and food systems. And also in the 21st century farming, ensuring food safety requires constant vigilance. So maximum residue limits, so-called MRLs, are vital benchmarks, and we will explore how these benchmarks will relate with biopesticides usages. We'll also be hearing from Vera Silva, and she will be presenting the SPRINT project, which is the acronym for Sustainable Plant Protection Transition, a global health approach, and its findings related to this issue. We will be exploring how this transition can affect the practical and regulatory aspects of the transition towards biopesticides, with a focus on ensuring both efficacy and safety. And I have to say, we are incredibly fortunate to have three leading experts with us today. First, we have Bárbara Oliveira, Director of Services for Means of Health Defense at DGAV, who brings unparalleled experience in plant protection, product regulation, and sustainable use, overseeing MRL's implementation. Then we have Helmut from Global 2000, who has been focusing in recent years on the link between the use of the so-called PFAS pesticide in agriculture and the spread of the forever chemical TFA, and we will learn more about this. And finally, we are delighted to have with us Vera Silva. She's a researcher from Wageningen University, known for her research on soil pollution and her expertise on pesticides assessment, and as a project scientific manager at the Horizon 2020 Sprint project. And our panel will discuss how a transition to biopesticide might be a crucial solution to the spread of PFAS, the forever chemicals, particularly TFA, and how it can be implemented safely while ensuring we continue to meet the food safety standards set by the MRLs. And as we progress, I'm trying to also just a quick note to remind you that to mention that Food for Sustainability is hosting the Healthy Soil for Life Summer School. So if you or anyone you know is passionate about joining a movement to save the planet and also promote human well-being through soils, we invite you to learn more and to apply. This could be an amazing opportunity, so just give it a try. And as we always start our webinars, we have prepared a couple of questions for you to start the warm-up into our topic. So as usual, I invite you to join our Slido, and I kindly ask the team to show us how we can join Slido. And what we have is a QR code, so please feel free to scan with your mobile phone this QR code. If you're not comfortable with the QR code, you can use a browser, a tab in your browser, and you can just type www.slido.com. You have a hashtag box. Just please insert the code F4S Academy And you're in, and let's see what the team has prepared for us as a warm-up to our topic on pesticides, the limits, the risks, and the future. So whenever you are ready, what is the first question? So the first question asks, I don't see anyone joining, so please, let's join Slido. So the first question is from a study in 2024, and this data reports to 2022. What is the estimated volume of pesticide sales in the EU? So this is a difficult one, very close figures. 310,000 tons, 322,000 tons, 360,000 tons, 375,000 tons. And this is figures reporting to 2022. And in 2022, the sales of pesticides in the EU fell to about 322,000 tons. And this is the lowest level since the start of this data series, which started in 2011. So this already represents a decline in 2022, which was the equivalent to 10% decrease compared to sales in 2021. And it's about 12% less than what we have in 2011. So we have seen a sharp decline in the more recent years. So the correct answer is 322,000 tons. It's still a lot of pesticides being sold throughout Europe. Thank you so much for taking part. I think we can move on to the next question. And the next question asks, which group made up the largest share of pesticides sales in the EU? So the largest group of pesticides in terms of sales. And again, this is a study from 2024 and reporting to data from 2022. So insecticides, herbicides, fungicides, and bactericides, copper compounds, which is the largest in terms of sales. And pesticide sales are reported for 6 major groups of substances. Fungicides and bactericides as one group, and herbicides, where the pesticides groups that record the highest sales volumes each year over the reference product is actually fungicides and bactericides. In 2022, these groups accounted for 43% of the total sales. So in terms of pesticides, what you use the most is fungicides and bactericides. That's what the most demand for these products follows. Thank you so much. And one other question. What percentage of the global pesticide market is represented by biopesticides? So within all the pesticides, what is the percentage of biopesticides in this group? We wish it would be higher, but is it 5%, 10%, 25%, or 50%? We have been discussing also biopesticides a lot. Do you have an idea? I have a tie now, so I'm going to kindly ask one of you to vote to make sure that we don't have a tie, because we won't have a winner. Okay, thank you so much to that 11th participant. So recent sources confirm that biopesticides currently represents about 10% of the global pesticide market. And this is according to a study published on PubMed from 2023 And this figure, in fact, aligns with the rapid growth of the biopesticides sector that has been experienced double-digit annual increase in terms of market share. So currently, this represents 10% of the whole market of pesticides. Thank you so much. Thank you for creating and participating in our Slido. It's been a pleasure. And now it's time to turn to our dear speakers. I will start with Bárbara Oliveira. Hello, Bárbara.
Hello.
You can share your screen whenever you're ready.
Yes.
Thank you.
It might take a few seconds for it to show.
Yes, we can see it in presentation mode, all working from this side. Thank you.
Okay, good. So maybe I can start now.
Yes.
Well, good afternoon. First of all, I'd like to thank the Academy for inviting me to share a few thoughts. Of course, in 15 minutes, we cannot say much on this topic of maximum residue levels and food safety. With respect to, of course, pesticides. So as a introductory illustration, you might probably know pesticides are presently extremely regulated and may be the most regulated compounds in the EU. And here in this quite simple picture, you can see that in fact there are proper frameworks and proper legal framing for all of the, let's say, all of the value chain of these substances. So active substances should be approved at EU level, and there's a proper framework for that purpose, based on a particular plant protection product that is supporting a dossier for that purpose of approval. And together with that, there are uses of that particular product that have to be considered, that have to be assessed. And the authorization of that plant protection product is issued at national level. So here we have an EU decision making, but also a national decision making when it comes to pesticides or plant protection products. But we do not stay here. We have also legal framework for the sustainable use of plant protection products. And it is within this legal framework where we have the proper training of all professional users. We have inspection of equipment used in the application of plant protection products, among other issues that in all serve to promote a sustainable use of plant protection products. And this is under the Directive 2009/128. And finally, within all this sustainable use, or as a result of this sustainable use, there is naturally the issue of consumer safety, besides the safety to all the users of the product, and the environment and animals, of course. And this is the issue on maximum residue levels establishment, and it's the main issue that we will talk about today. So in summary, setting MRLs today is regulated under...
Bárbara,
sorry, yes?
Sorry to interrupt. Are you moving your slides?
I am, yes.
Yeah, because it's not showing from this end. We are still in your first slide.
Oh, what can I do to... Maybe you can share the slides instead of myself? Because
yes, sure.
I am moving the slides.
You are, okay, no worries. We will do that from our end.
Okay, so I will stop sharing my presentation and start again. Because I was I was seeing them moving on.
Hold on, just I will try to share from my end. Just this.
I have here and already.
Okay, thank you,
presenting.
Fita. Okay.
So maybe we can move already forward. So as I was saying, the appropriate regulatory framework for maximum residue levels setting is Regulation 396/2005. And it has a number of different annexes for those more interested in knowing in more detail how this regulation works. These annexes set different are let's say technical setting or the food commodities for which there are MRLs that have been set, or even the substances that are do have MRLs already set, substances that do not need MRLs because of their particular characteristics, substances that have MRLs set at the minimum level, that is the limit of quantification of the available methods of analysis of that particular substance, etc., etc. So for more details and for those who are more interested in this issue, you can consult this link that I show in the bottom of the slide. Next slide, please. Now, what are MRLs and why are they set? First of all, there's a legal issue that permits, in fact, that food produced with the use of plant protection products, so pesticides, can be moved freely within the EU, so within different member states, but also from the EU to third countries and vice versa. So there has to be a legal limit for this purpose, for the purpose of free movement of these particular goods. But also they are set based on agricultural practices. And these agricultural practices, by definition, because we are using plant protection products, should the residues that are resulting from the use of a particular plant protection product have to be as low as possible. So the MRL is established based on the lowest exposure possible, and as long as it is safeguarding the health of the most critical and vulnerable groups of the population. So in a simplistic approach, this is the definition of an MRL. In other words, please. Yes, in other words, as I said, there is an agricultural practice where we talk about, where we consider the application rate, the number of applications of that particular plant protection product. So all that is associated to the use of a particular plant protection product against a particular disease or to control weeds at a particular dose, number of applications, or on a particular crop, and the timing of the application. So all associated to the agricultural practice. And the most critical one, meaning that different member states may have different practices, And for the purpose of setting an MRL, what we need is the most critical one, so that we guarantee that the agricultural practices that are less critical also are covered by the MRL that will be set. On the other hand, as we are talking about residues, residues that are the degradation products or the active substance itself, resulting from the metabolism in the plant or in the animal, and the exposure at the end may result in residues. And so we do need, of course, the setting of particular tests and studies to assess the behavior and the dissipation of the residues of the substance or degradation products of the substance. And for that, trials are conducted for this purpose. And also there's the issue of safety means we do need to consider toxicity of the particular substance and or its metabolites. So these are the three main aspects that are incorporated when we are setting MRLs. Next slide, please. Now, who are the actors? Who establishes MRLs? At EU level, we have the participation of member states as assessors, as evaluators of good agricultural practices and evaluators of dossiers for either the approval of the active substance or the authorization of the plant protection product. The assessment is made, as I said, by member states, but it is also assessed. The work done by the member states is assessed at the EFSA level. And EFSA, on that basis, reviews the assessment made by member states and proposes and issues an opinion on the proposals of setting MRLs made by member states, and this is discussed at particular standing committees at the Commission level for the purpose of setting or changing MRLs at EU level. MRLs at EU level are subject to the scrutiny of the Parliament and the Council. So there is a small image in the slide, but it essentially shows all the procedure from the assessment by the member states and proposal until the publication of the regulation setting MRLs. But also there are maximum residue levels established at international level, and these are established under the rules of Codex Alimentarius. Again, there is a stepwise procedure for setting MRLs or Codex limits at international level. And if you are also interested in knowing a little bit more, you can, of course, access the relevant links of Codex Alimentarius or even at the EU level. So the EU Commission platform. Next, please. Now, when we talk about MRLs and food safety, what is the let's say the state of play? As I said, the legal framework is the regulation 396/2005, and under this regulation, besides setting MRLs, there's an important aspect that is to monitor the compliance of the practices, the agricultural practices, so the use of the plant protection products, in member states compliance with these MRLs, because, as I said, they are legal limits. And for this purpose, official controls are set by all member states within a multi-annual coordinated control program that is also discussed and decided at EU level. And together with this multi-annual coordinated program, there are national programs for the control or for the monitoring of MRLs, so the compliance with MRLs. Presently, more than 600 pesticides are already subject to controls, to analytical controls by member states. Of course, some member states have laboratories that analyze more than these 650, but others less. But in average, we can say that more than 600 pesticides are presently analyzed at under these programs, and 370 food products. So both animal products and plant products. The results of this monitoring, so EU monitoring and national monitoring, are collected by EFSA. So member states have to each year submit the results to EFSA, and EFSA compiles all the information and produces reports on the controls carried out at EU level. Of course, samples, there is a risk-based selection of the products that are subject to analytical controls, and they are and these samples reflect the market availability and origin of the products. If there are cases of non-compliance with the MRLs, member states have the power to implement administrative actions throughout the whole chain from the producer until the retailer of that particular product. But we shouldn't let's put it this way. There is also there are also official controls at border line. So at border control of produce that is imported to the EU, and this is within different legislation. And there's one thing that is normally people are not aware of this, but when we are controlling import food from third countries, if these are plant products, animal products are non-conform, the product do not enter the market, so they are rejected at the border and do not enter in the EU. Next slide, please. So just to share what is the state of art in terms of controls of MRLs, compliance MRLs. The last numbers we have, they're publicly available, so all this information is available at the EFSA website. And overall, we since at least 2015 to 2022, more than 95% compliance with MRLs that are set. So this means that there is generally we can consider that there's a low risk to the EU consumers, as shown in the results of the monitoring of MRL compliances. Data from 2022, and this is multi-annual coordinated control program and national control program. We are talking about more than 110,000 samples collected, both from animal and vegetal origin, with compliance of greater than 96%. So more than 96% of samples were below the MRLs, the published MRLs. More than 37% of the samples contained quantifiable residues, but not exceeding the MRLs. 3.7% of samples were in fact above the established MRLs, but this does not mean necessarily they were non-conform, because the non-compliance of a particular residue is associated with the reliability of the analytical method. So, and how to assess this is based on the analytical uncertainty. So you can only consider a non-compliant residue level if you consider or after taking account of the uncertainty of the method. So in this case, although we have 3.7% samples above the MRLs, in fact, only 2.2% of the samples were non-compliant with the established MRLs. Considering only the multi-annual control program coordinated, so at EU level, and this is more than 11,000 samples. The non-compliant samples only represented 0.9%. Next slide, please. So this is also a figure that shows the distribution between samples with residues below the limit of quantification of the methods, or between the limit of quantification and the MRL, samples above the MRL, and samples that were non-compliant, with the products for which the residues of pesticides were found, and this data is coming from 2022, and this is also available at the EU EFSA website. Sorry. So what you see here is essentially the majority of samples are below the limit of quantification of the methods. Next slide, please. So assessing risk when there is a sample that is non-compliant, considering also the uncertainty of the method, there is a risk assessment that is needed. And this is both acute risk assessments, where we consider the acute reference dose, so a toxicity parameter, and the highest residue data that we obtained in the monitoring. But also a chronic risk assessment is made, considering another toxicological parameter, that is the acceptable daily intake of a person, with a number of criteria considered, and considering the mean residue data obtained and the national food consumption data from that particular member state. The procedure is available and is based on a model now. So the calculation is made under this particular guidance, and this is a primo model that you can use to calculate the acute and chronic risk. Next slide,
Bárbara,
please.
just to
Sorry.
say that we are over our time, so
Yeah, it's
because
just one or more two slides. I think this one is the last one. But also we do have cumulative exposure, and this means exposure to consumers on the basis of products, so food, where multiple residues may occur. This is not as frequent as one might expect, but nevertheless, EFSA and the member states are now working to find a proper model to assess and foresee what would be the risk associated to exposure to multiple residues. This is a probabilistic approach instead of a deterministic approach, such as the one that is now carried out with the primal model. But for more information, you can also follow the link in this slide. And I think this is it. Just if you can.
Thank you. Yeah, exactly. Thank you so much.
Okay.
Very, very interesting. And thank you for a very clear presentation. The topic also of combining multiple substances it's quite critical. So we will try to, for all those that are interested in all this valuable information that Bárbara just shared here with us, let us know. If we have permission, we'll share the presentation. I have one question, and I will invite our audience also to use Bárbara's time here for a question. So in agricultural practices, many pesticides apologies, are part of a broad chemical families, sorry, which can lead to similar residues or metabolites appearing in the final products. So considering current pesticides residual legislation, are MRL values defined only for each specific active substance that is authorized or and then analyzed, or is there regulation allowing MRLs to be established for chemical families, including metabolites common to several substances within the same family?
Well, the issue is more when the assessment is made is pesticide per pesticide. However, all possible commodities where that particular pesticide is used are and can contribute to the final exposure of the consumer. So meaning all the food commodities that are within the diet of that particular population are considered in setting the MRL and assessing the risk. So it's adding exposure from that particular pesticide in all the items that one can consume. So in the end, it's not a single exposure. It's an exposure that is coming from the different items that are ingested.
Okay, so it's always from the consumer perspective rather than the chemicals that are used. So it's mainly to do with the exposure that the consumer will have to the substances.
Of course, when you have substances producing the same metabolite, when you are setting MRLs, this is also taken into account.
Okay.
So every different exposure possibilities to that particular pesticide are taken taken into account when setting the MRL.
Okay, thank you for that clarification. I see that Helmut is also jumping in the chair. I will give you the floor in just 1 second. Just one final question just before we move on. And we've been addressed in past session cycles, biostimulants. So I'm rather curious about the interactions between pesticides and biostimulants. So the question is, are we aware of the effect of biostimulants on the persistence of the pesticide active ingredient in the crop or in the environment? And do we also know anything about the potential for biostimulants to chemically alter the pesticide molecule or break down its pathways? Have we looked at this interaction between pesticides and biostimulants?
Well, first of all, I must just clarify that biostimulants are not within the frame of the Regulation 1107 on plant protection products, on the placing on the market of plant protection products. They are within the frame of the regulation on fertilizers. And because of that, they no longer are assessed within the regulation on MRLs. So I would say that it is quite difficult to address the possible, as you said, interaction between the exposure to biostimulants and pesticides for the moment, for the time being.
Okay, thank you. That's something that's it's often brought about by practitioners wondering if there would be any synergistic or detrimental effect. Bárbara, the time flies. I need to move on. We have a couple of questions in the chat. I would truly appreciate if you could just look at the chat. I will now call to the floor, to the stage, Helmut Shannon, who is going to tell us a little bit more about PFAS. What are they and why are they called the forever chemicals? Helmut, the floor is now yours.
Yeah, thank you too for inviting me. I will now try to share my screen with you. So. Okay, it's here.
We have tried this before. It works, so it should be working now also.
I hope it works now. Can you see?
Yes, we can see the presentation.
Okay,
yes,
that's
perfect.
Great. So yeah, I would talk to you about something that is not so well regulated as most of the pesticides, as we have heard by Bárbara before. It's a molecule, and I will talk only about molecule, despite the fact that we are, of course, surrounded by a number of molecules, pollutants in our environment, in the food that are regulated. But there is some reason to talk about this in a special way, and I will come to that. You can look into this molecule. Its name is TFA, trifluoroacetic acid, from two different perspectives. One is the perspective of a pesticide metabolite, because it's the end product, the final end product of some pesticides, some synthetic pesticides. It's around 15% of the now on the European market used synthetic pesticides that produce or set free this metabolite. But you also can look into this metabolite from the perspective of a simple pollutant that is the final degradation product from so many other substances, forever chemicals of the family of PFAS. I think we talked about PFAS already. If not everyone is familiar to this, PFAS is perfluorated, polyfluorated, and perfluorated alkyl substances. This is a very big group of more than 10,000 chemicals that is used in so many everyday articles that we use, like non-stick cooking, like food packaging, also pesticides, as we have heard, fire foam and things like that. So substances that are very usual, but also very problematic for the environment, and percentage around 2,000 of these substances are known or estimated to be precursors of this small substance. And that's the reason altogether why this substance is very much come from in the spotlight, or it's on the way into the spotlight, and it's also something that from a perspective of regulation is discussed now a lot. I will use I hope the next 10-15 minutes to talk about once the sources for this TFA PFAS, the distribution, the possible health risks, and the measures needed. The sources are, as we said before, I will make it different. I will say what is not the source, because there are many PFAS like this one. This is, some might know it, it's the most famous and maybe one of the most dangerous PFAS substances, but this is not a precursor of TFA, because this substance for itself is a forever chemical and it stays forever, and it's very harmful to the environment and to health. And as you see from the chemical structure, it's from the same family than TFA. TFA is, if you look or see it like that, the smaller brother. It has only one perfluorinated carbon atom. The other substance had 8. Therefore, it's called octanoic acid. So we go back to this degradation product, which is the smallest PFAS, and it's the final degradation product of 2 major sources. One is what you see above is the so-called F gases. And you see here also the same chemical structure, a carbon atom with 3 fluor atoms. And when F gases in the atmosphere are oxidized by the ozone, by the ultraviolet energy, then TFA is one of the products, and it comes down with the rain. The second substance that you see below is one of around more than 30 PFAS, pesticide active substances, currently authorized under the EU pesticide regulation. This substance has now been decided not to be reauthorized. It's flufenacet, but not only because it's making TFA, also because it's an endocrine disruptor, which was now found to be the case. Both are precursors. That means mother substances that in the environment will inevitably set free TFA. And because TFA is itself a forever chemical, it is actually one of the most stable, if not the most stable organic chemicals that we do know on this planet. So there is no way to get rid of it when it's once in the environment. And F gases have been used as a result of the Montreal Protocol to get rid of the chlorfluorinated gases that were destroying the ozone layer. And since then, TFA is increasing. So since the 90s, PFAS pesticides are also used since the 90s. So there is an amount of TFA in the environment that increased over 3 to 4 decades. And we did, and I think it was the first time that in Europe, an NGO, or actually that data on TFA have been investigated in a number of European countries, and it was publicly presented in a press conference, and this happened in 2024, in summer last year, by a group of NGOs, which I was involved. I was actually coordinating this testing. We were not the first to test it, but we were the first to talk about it. And what we found was extremely surprising also to us, because I will come later to the concentrations we found. But as you see here, different rivers in different European countries all have TFA, and I can bet with you, you will not find any river, any lake on the whole planet where you don't find TFA, because TFA comes down with the rain, and therefore it's everywhere on the surface. But, and this is even more concerning, we also found it in tap water, and tap water in many European countries comes predominantly from groundwater, and groundwater normally is more protected against chemicals, against pesticides, because of the filter function of the soil, where chemicals are normally absorbed and later degraded, destroyed, metabolized. TFA is neither absorbed, because it's one of the most mobile chemicals that we know. You even cannot get out of water by usual water filter techniques, because it doesn't, it's not absorbed to anything. And the second thing is it's not broken down by anything. So it inevitably ends in groundwater, and that's the reason why we find similar concentrations in groundwater and therefore in drinking water than we find in rivers. And it's even so mobile that sometimes it reaches the deep or contaminates, at least. We do not know exactly where it comes into mineral waters, but we found it also in a number of mineral waters, which by law should come from water sources that are protected against any human impact. So the next thing that I want to share with you is a comparison of the TFA levels. TFA, as I said, is a PFAS. It's one of member of the family of the forever chemicals, per and polyfluorated alkyl substances. It's the smallest one, and as these data show, it's by far the most widespread. What you see here in this pie chart is a comparison. The blue is TFA and red is the rest of PFAS substances that are found in water, that are looked for in water, and that are regulated under, or will be regulated under the Water Framework Directive and under the EU Drinking Water Directive. But TFA is not regulated as a single substance, and this is a problem when you see it's the most occurring one. And this is not only true for comparison of TFA with all the other PFAS that we are able to measure. It's also true, and I said it in the beginning, TFA, you can look at TFA from the perspective of a PFAS and also from the perspective of a pesticide. And since TFA is actually the everlasting metabolite of more than 30 active substances that are used around the EU, and it was more than 40 a few years ago. So TFA is also or should fall under the pesticide regulation. I will maybe come to that. If not, then you should ask me. We now want to have a look on the concentrations, what we found, and not normally you take this in relation to legal limits. Actually, there is no harmonized legal limit for TFA, because it has been, if I have not said it, it has been really under the radar of regulatory scrutiny, of surveillance, almost all over the European Union for many, many years. The first time that I'm aware of that an authority, it was Germany, and it was just per accident, because they were informed from a student who found TFA in a drinking water supply, and they were asking, what is this, where does it come from? And so the thing became more popular in the German UBA, Environmental Agency, and they started to look. But it didn't happen so much until now. But in 2021, something happened. A chemical that, a TFA that has been seen, or at least there was some kind of wishful thinking that TFA, because of course one knew that something is accumulating there, but the wishful thinking was that it's a harmless substance. And industry was really putting a lot of effort in telling this tale, this myth of TFA being not really a PFAS. Okay, other PFAS are dangerous, but only the big ones, the long chain PFAS or the medium chain, but not such small chain PFAS. And it acts completely different. And then Bayer was forced under the European Chemical Regulation, also under REACH, to do a study on reprotoxicity. So actually it was a teratogenicity study, which is done with rabbits. And they look if the dosing of TFA or substance in animal experiment with rabbits has any effect of the offspring. And in this case, the offspring, the embryos, the fetuses have been had severe malformations of the skeleton and even more severe of the eye. And this in all those groups, which is a very, very concerning result. And that was somehow a starting point to think about how to deal with this. But this happened only in 2021, that the study was officially submitted to the EU Commission, to EFSA, and to the member states. And since then, regulatory agencies are thinking about how to deal with that. One agency in the Netherlands has at least developed a drinking water limit. And what you see here is this drinking water limit. It is the most precautionary limit that exists in the moment in the European Union. Other member states don't have any limits, or other member states like Germany have quite high limits, which come from an earlier time when we did not know anything about this teratogenic effect of TFA. But that's not the only limit level that should be or could be applied for TFA, because there is also another. I show it now. It's 500 nanogram per liter. 500 nanogram per liter is in the EU drinking water directive, with the level for the PFAS total, it's called. So it's all PFAS other than the 20 PFAS that are regulated specially. And therefore it includes also TFA. But as we see here, when we look into the tap water levels, it's not realistic that this level of 500 nanogram per liter can be applied, because that would mean that so many drinking water suppliers would have to close. And unfortunately, we have to expect that the concentrations of TFA will rise in the next years and the next decades. So, and now I show you something that is even a smaller level. This level comes from the context of pesticide regulation, because pesticides can only be approved if the pesticide active substance does not contaminate groundwater, or is not expected to contaminate groundwater above this 100 nanogram per liter, 0.1 microgram per liter. And this is also true for a metabolite of this pesticide, in case this metabolite is toxicologically relevant. And the problem with TFA is, or was, or is, that authorities like the EFSA just failed, missed to look into TFA. Is it toxicologically relevant or not? So one PFAS pesticide, one precursor after the other was authorized and reauthorized without looking into the toxicology of this metabolite, which is a forever chemical, which is clearly accumulating in the water circle, and which now, 30, 40 years after the first PFAS pesticide came on the market, EFSA was not even existing then, turns out to be toxicologically relevant, which has meanwhile been, it's important to say it here, also confirmed by the European Commission that it has to be considered a toxicologically relevant pesticide metabolite. So TFA in the biosphere, why do we ask this question? It's because, we all know that life is water, water is life. We all consist of water, human beings around 65%, I think. And therefore, if all the water is contaminated with TFA, then we are too. And also the plants out there and everything. And there is actually not much data. That's also something that is unbelievable. It's, as we wrote in our first report, TFA is the by far most widespread man-made chemical in the global water cycle. But there is so less data on its occurrence in food, in plants, in animals, and also on toxicology. That's really a problem. So we are happy that some people, and this was is something, actually we did the same testing, so my organization and a group of other organizations together, not knowing that a professor in Germany did it already 1.5 years before, looking into TFA in new and in old aged wines. Wine is the only agriculture product that you very easily get samples from harvests that go back to the 1980s, 1970s, even 1960s. So you can just look like in a time capsule. How was the environmental situation in 1970? And we did look at this. I do not present our data because we will present them for the first time in the press conference next Wednesday. So maybe the invitation will be shared by the organizer for interested people. What I show here is what this professor from the University of Freiburg found. And you see there was a very slow increase of TFA starting from the 80s, 90s. The Montreal Protocol was a very clear element, but also the increase in PFAS pesticides. And there is meanwhile a very sharp increase since around 2010, so since 15 years. And that's what we found in the data that we had the same. And this fits also to the only data that have been conducted officially by a governmental institution. In this case, it was the European Commission that commissioned a reference laboratory in Germany to investigate food, different kind of fruit, vegetable things for TFA, and this was done in 2016, 2017. And the levels they found in wine just fit into this figure. So in 2017, they found around, I think, a median of 50, and we now have a median of 110. So there's really almost exponential increase. So that, of course, leads to the question, is there a possible health risk from a substance that is so ubiquitous in everywhere? Yeah. And actually the data situation, as I said before, is not satisfactory. But what we know gives, of course, cause for concern. And as I already said, there is proof of teratogenicity in an animal experiment, which is very, very clear in its outcome. And this had already led here. He was the leader of this consortium who made this study to self-classify underreach TFA as a substance that is reprotoxic as a group 2 with what means actually that it's suspected to put harm to the unborn child. And that doesn't say anything about, it says something that it's suspected, but there's no proof that it's dangerous for humans. And it's also always a question of the dose. And this is something that now EFSA and to some degree, I think also ECHA is looking into. ECHA more from the hazard-based, EFSA from the risk-based perspective. But I think the answers they find are important because TFA has been shown to also accumulate, or there's evidence for accumulation in human blood, where it's found in amounts 70, 80 times higher than in water. There's the second report on TFA in drinking water. We also were looking into what risk assessment could give us answers and to deal with the question, because it's about in the end also setting MRLs MRLs limits for drinking water, but in the end it should also be MRLs for food and vegetable. And we do not know actually if, as it is already the case with other PFAS, contamination in some food species, like for example fish, with the PFAS that I have showed you. In many regions of the world, it's not safe anymore to eat fish because of the amount of the load of PFOA, the big brother of TFA, or the load of PFAS. We do not expect TFA to be in fish or animals in that huge, I mean, maybe in higher amounts than the other chemicals, because also in human blood, we find more TFA, although it's not bioaccumulative, than all the other PFAS together. So this is the finding of the two studies that I've showed you before. Not only that there are relevant amounts, the amount is higher than all the other PFAS together, but, and that's the good news, we do not expect TFA to be as by far so harmful to health as it is the case with PFOA. So there is some kind of a difference in potency, but I think it's important to have a very careful look. And
Helmut,
I think the time is, so the measures required, I will finish now, to get this curve a bit flattened. This is from a very important publication warning that TFA is a threat to the global boundaries, planetary boundaries. So to deal with that, we should ban PFAS pesticides as the major source of contamination of drinking water. We should ban F-gases as the major source globally of TFA contamination by far. And of course, we need safe limits for TFA in food. Thank you for your attention.
Thank you, Helmut, for bringing to our attention such an important issue. And as I noted here in the chat, there are some participants that thought they knew a lot about PFAS, but they were not aware of TFAs. I think you also mentioned throughout your presentation why this is such a recent topic, the way it was discovered, and the most recent studies that have been done. So we are looking for the developments in terms of where all this will lead, and particularly the solutions that we have to deal with a solution to such a pervasive chemical in our planet. Also, we have a question here, and someone that probably has a very good site, because someone spotted that Portugal is not on your list for the presence of TFAs in tap water. It would be interesting also to know if you had figures from Portugal. Just one final question before I move on. So you clearly mentioned that TFAs bioaccumulate in plants and persist forever. So what is the impact of this in the safety claims of, for example, organic products, if TFA contaminated rainwater or irrigation water is present all over?
That's a very, very important and good question. We did look into a few organic wines in our testing that we will present next week. And to spoil this, we found TFA in similar amounts in the organic wines than in the conventional. Also, the organic wines didn't show pesticide residues, the conventional did. So the problem of TFA is, of course, and that doesn't say that it doesn't come from pesticides, but it's not only the direct use of pesticides, meanwhile, that brings TFA into food chain. It's the ubiquitous, ubiquitare
Yes.
presence, yeah, of this forever chemical. And there is some data from this German professor who dig deeper into this question, looking a timeline of old and new vines from a very specific farmer who worked organic for decades. And there the TFA levels were lower than in just average organic wines.
Mm-hmm.
So there is a link. Organic wines, organic food, we can extrapolate, yeah, has a bit less TFA than conventional, but the difference is not that big as we would wish. That was also the outcome from the only official study that I was talking about in 2017. There also organic food was about 30-40% less contaminated.
Okay, fantastic, Helmut. I really need to move on, but I hope that you accept our invitation to come to a future webinar to tell us about the solutions to this huge problem and how we can, ensure that we, at least our bodies and the choices that we make are free of TFAs. We have a question for you in the chat, so I kindly ask you to direct your attention to the chat, and I'll move to Vera Silva. Vera, she's a researcher from Wageningen University. Hello, Vera. And Vera is going to tell us about the Spring project and hopefully pointing us with a lot of solution on how we can do this transition more smoothly and in a better way. Vera, the floor is now yours. You can share your screen. Thank you.
I hope you can see it now.
Yes, it's perfect. Yes. Thank you.
Super. Well, thank you, first of all, for the invitation. I'll try to keep short, considering the timeline. And of course, if there are any follow-up questions, just come. Yeah, so I'm talking today about work that we do in the Sprint project that is indeed about sustainable plant protection transition. I hope you can see the slides moving now. So this is Horizon 2020 project, 5-year project that is reaching its end this summer. So we do have a lot of data and key messages and insights. So that is a good part. That does not bring a lot of solutions though, kind of disclaimer. So this project involves 29 partners across Europe and in Argentina, also to bring here the import feed towards Europe. And it's coordinated by us, by Wageningen. But well, it will be impossible without all the partners, and I'm just leaving here an overview of our partners so you can also understand the diversification of the expertises that this project requires. And because, well, on one hand, because we are talking about health and we are talking about global health, so we do approach impacts of pesticides on environment, but also on plant, in this case crops, also livestock and human health. So we do try to understand indeed the whole holistic challenge. And the second part of the project aim relates to transition pathways towards more sustainable plant production. So some highlights of the project, well, one of them is indeed about our data sets. We have done intensive analysis of pesticide residues across different environmental and biological matrices. We have done risk assessment in mixtures. So, and we have done it also on non-standard ecotoxicological endpoints and in native species. We have also invested quite a bit on these links and bridges, so including model chains and development of a wind erosion module. And they come all together and also as a potential for upscaling in our risk toolbox, which I'll touch upon in a second. So again, it's not so fun, this type of slide, but I think it's also important to understand a bit the flow of the work that we do. And you can see in the core of this work package structure that we have 4 work packages that derive most of our data. So work package 2 that is on field, so the sampling and the characterization of health status with questionnaires data. And then on work package 3 that is on exposure is a modeling based work packages. Work package 4 is on ecotoxicological and toxicological assessment, so all the lab and all this testing of these mixtures. And then work package 5 combines AI and the different spatial tools to aggregate this information to also inform on risk. And all this supported by cost-benefit analysis, work package also on transition, ethics, and so on. So maybe starting at the beginning, where the biggest core of our data and that define a bit the direction of the work comes from, that is from the field. So in 2021, during COVID pandemic, we managed to collect samples across Europe and in Argentina, and this covered, so we have 11 case study sites. We cover the main crop types, and in each one of these case study sites, we have both conventional and organic farms. So we wanted to assess distribution across these different farming systems. And in each one of these fields, we collected several samples. So as you can see in the scheme in the left, we collected samples from humans, from urine, blood, feces. We asked them to wear wristbands, also to address thermal exposure. We did nasal swabs for microbiome evaluations, and we also had food analyzed. So we asked this the DPA, the duplicate portion analysis, so where the participants provided us an example of everything that they have ate, and we analyzed it for pesticide residues. Ecosystems include soil, water, sediments of these water bodies, fish. We analyze the fish fillet, for instance. We analyze also pesticides in indoor dust, outdoor dust, in earthworms, in feces of bats, and we also look into diversity of insects, ground-dwelling, flying insects, and also in microinvertebrates in this water body. So we have different lines. Pesticides, the chemical part was the core, but we have different lines of information from diversity, from microbiome, that we combine to indeed infer on the health status. So just also some pictures of the work. So it was interesting that most of it was actually conducted by our researchers, except of course blood collection that we required, like vets and nurses, but most of it was also interesting for us to learn new methodologies and training on it, but it was rather holistic and comprehensive. And here, not entering into details, but I remember from the first presentation that we were talking about MRLs, about 600 pesticides. Well, we didn't analyze that many, but we did select the ones that we consider priority for our locations and our crop types, and we managed to analyze in each of these samples 209 pesticides, and these included currently used pesticides, legacy pesticides, the old ones, and also active substances and metabolites. So it was all mixed to understand indeed contamination status better. And well, some examples of what we retrieve from this. So first on the number of pesticide residues. So here I give you a glimpse of the number across environmental matrices. So I'm not going to the human and livestock, but here on the environmental. And you see that in soils, crops, and air, where we did have farms, conventional and organic, we do see that although conventional ones have higher number of compounds, there are still residues in organic farms as well. Also, something that came as an outstanding result was that indoor dust actually had a high number of residues. We had samples with more than 100 pesticide residues, to be clear. And the levels of pesticides followed a similar pattern, so also rather high in indoor dust, where partially explained because of slower degradation under such environments. So we also look at like the holistic way and try to understand also where a specific pesticide appears. So we did this kind of matrices to understand indeed not only into the field farm context, but environmental one, where can we find it, also to understand the widespread contamination. And we did this for the different types of compounds, the ones that are approved, ones that are candidates for substitution. So that was also particularly interesting to understand where they are, but also for the banned ones to see if there are still legacy impacts of these compounds. Because we did have information about pesticide use, we also managed to compare our measurements against predictions, and these highlight some often mismatch between measurements and predictions, and raises some concerns about decisions making based on such predictions. But it's also very hard to make clear patterns among regions, among type of pesticides, because it's indeed a rather complex data set to work. And what we are doing now at wrapping up of the end of the project is indeed to work on the integration of pesticide findings with other health indicators, namely microbiome, diversity, biomarkers. We also analyze biomarkers. So we have done individually, and now we are working on the integration of all these lines of evidence to make indeed a better, more comprehensive health assessment. We are also thinking about the potential of this monitoring data, and one of them is taking advantage of information about occurrence and also the hazard characteristics to identify priority watch list compounds. And well, now, for instance, with the soil monitoring law moving forward, that could also be something that could provide additional information to the discussion about the priorities. And you can find the results of each piece of matrix, like indoor dust, on soils, and you can find all of this via the project website. We also have published the study protocol and so on. So feel free to dig a bit around and write me back if something is not clear. So we are now in the last year of the project. What are we doing besides this integration is on the interpretation of risk findings. So we went to the field, we analyzed the samples, we saw the compounds, and then we pick up on these mixtures, the most prevalent mixtures, and we test them. So we test them in a battery of terrestrial and aquatic organisms. As I mentioned before, standard ecotoxicological organisms, but also native species. And we test also different type of endpoints, some of them also more not towards necessarily mortality and reproduction, but more subtle as early signs of toxicity. What have we seen? So preliminary findings is that indeed mixture, our results corroborate that the mixture leads to higher toxicity than just adding the different components. So if indeed we look at the levels of each one of its components, sometimes toxicity would not be expected, but we did observe it. And we also noticed that the more comprehensive the assessment is, the highest likelihood of finding risk. So once we consider, for instance, just the earthworm species, 5 out of our 11 case study sites show a risk signals. By including a second earthworm species, it increased to 8, and by including also other terrestrial organisms, all of them actually show some degree of hazard and risk. So it's also important to keep the big picture in mind. That is challenging, yes, but it's also be mindful that, especially in regulation and policy making, that there are different lines that should be accounted and provide complementary information rather often. Well, for time and also because it's not really my expertise, I'm just giving brief details about also the work that we did about the effects on animal and human health. So here we did use a tiered approach. So we didn't, so we started with the in silico with the top 20, and here it was again started by the field results, but also some hazard information of these compounds, and also like the knowledge about their interactions. And then the ones that show higher toxicity, we move to the next phase about in vitro testing, and then the ones that again with outstanding results were tested also in vivo testing. And also here we had standard endpoints, but also more novel endpoints that included, for instance, organoids testing. So to understand also a more mechanistic way how these compounds, these pesticides are affecting the organism. So we have all these results and we are trying to wrap them up. And we have this toolbox, which is literally a box of tools. So that can serve different purposes, from awareness raising, but also for predictions of distribution and risk. And we expect them to be useful for different type of end users, because we do believe that indeed this transition, it doesn't go just by farmers, not really, not at all. It indeed includes the whole the food chain and all the system. And that is something that we have invested also quite a bit to understand, on one hand, the lock-ins and barriers across our case study sites. So we also saw some common patterns by region and by crop types, but we also explore with them not only what is hampering them for further, for more sustainable practices, but also like how this transition would look like in practice. So the building blocks, again, gradual building blocks that they see within their context and with their all restrictions and opportunities, how this transition could look like. Also in line with this ambition of reducing pesticide use and risks. And we came up indeed with some different priorities in each one of our case studies about what our stakeholders identify indeed as next steps. And that could indeed be also picked up for cost benefit and more tailored programs for these specific regions, but others with similar management and practices. This is my last slide. That is our kind of motto of all aboard on the Spring Translation train. That is indeed, we rather often deal with, we start in the field with outcome, we look at the policies in the beginning, but there is the whole in between from the consumers, as we also heard here today, and the regulators, and there are a lot of steps and a lot of aspects that we should be indeed mindful about their role and their contribution to this challenge that is about sustainable production and also sustainable use of pesticides. This is me. Thank you.
Thank you, Vera. Very interesting work that you've described here, and I'm sure now you have a lot to do in wrapping up and ensuring that, you know, the key message are clearly communicated and actionable to each of the stakeholders. Funny enough, you mentioned in one of your slides that farmers demand training. As part of the academy, we always try to provide, you know, that training to farmers, but it's the take-up of this training is not huge, but it's something that comes up again and again and again. So it's definitely something that we should also continue looking and finding more effective ways of making sure that the knowledge reach farmers. Two things caught my attention from your presentation. One thing was that graph that you showed about the presence of pesticides, and indeed soils weren't at all the most where you would find. So that points me to the belief that, you know, the soil microbiome and healthy soils can actually degrade these molecules and can be somehow beneficial. So again, take care of your soils.
Yes.
They are doing
But
something.
a disclaimer there, indeed, indoor dust was the worst, but does not mean that soils are in great condition. Okay, so indeed we did find still a high diversity of pesticide residues there, including in organic farms. And indeed, in soils, it's extremely challenging to give a meaning to the levels because of all these, well, and the good part is all this diversity and all these organisms, and we don't have actually a lot of information about the toxicity towards most of these organisms. There are interactions among the pesticides with other contaminants like PFAS, with plastics that are also commonly used in agricultural practices, and all of these affect transport, toxicity, availability, so it becomes rather complex. It's not only like just look at the levels, but it's like, again, as a whole, it might become rather complex challenge. And I hope that indeed this current situation of the soil monitoring law also highlights the problem and the urgency of protection of soil resources.
Yes, and that was quite clear when you mentioned the risk detection and where that pyramid where you were adding more animals and the chemical substance were appearing more and more and more. That was quite interesting. I think we have very good knowledge here. Also, you pointed for the combination and the mixture effects of different substances, which is something that is coming out, and researchers are actually looking for more and more about those insights. So hopefully we can know more about you. And I will just take one last minute to ask you, Helmut and Bárbara, based on what we have discussed here, what do you think are the challenges to come in setting our maximum residue limits for pesticides, considering their persistence and how difficult it is to break them down as new ones appear, as new ones that have not been monitored, as more measures come around and show that actually we're not really targeting the entire picture. So what do you think will need to be done in the future to ensure that MRLs are actually measuring, safety for all the consumers?
Well, if I may be the first to respond, I think we can only go so far as the technology we have. First of all, and the more we want to know, the more technology we need to do so. Of course, the new challenges are to assess the cumulative effects and the synergistic and additive effects of exposure to multiple stressors, and not only pesticides. And pesticides are not only coming from use in farms, of course. So where do we stop and what do we consider? This is and how will we use the information we collect? Because well, I have a colleague that is always saying there's a difference between what we want to know and what we need to know. So at some point, the decision makers also have to set a line between what is useful in terms of policy making and where do we set the level between the need to produce, to have economic activities, and the protection of humans and the environment. So where do we set the line? And this is, for me, is the greatest challenge.
Yeah, and in good Portuguese, we have the saying, the ótimo is inimigo do bom, and sometimes we need to be, but it's important to be aware of those trade-offs, and it's true that there are other things involved also, and the farming is an economic activity, and we shouldn't forget that. Thank you. Helmut, Vera, any comments?
Yeah, maybe I can just add on that what Bárbara has said. I would say it's not only about what we want to know and what do we need to know. Sometimes it's also about what don't we want to know. And looking away, this don't look up theme, this is something that is very true for the story of PFAS in general, and even more for the story of TFA, because for me it's still a mystery how this could have been under the carpet, under the radar for 3 to 4 decades and involving in such a big mess. Yeah. And also, what do we need to know? I think I do not feel very safe, I have to admit, or very well protected by MRLs because of the issues that are around what we actually know about the toxicity of pesticides, of single substances, also of combination, everything that you have already raised. And sometimes I think there is a very sharp and sometimes absurd contrast between the detail we sometimes have, for example, when we look into MRLs for processed food, yeah, like apple juice, orange juice, where we look into the MRL of the orange, the apple, and then we have processing factors, and we have different processing factors for different active substances, and there is a lot of detail for very limited. Yeah, I think we would not need that when we do not even look into other much more relevant contaminants that are also under the pesticide regulation, like, for example, I think TFA is really a very good example, but there are also other pesticides that we could refer to where, yeah, there was evidence of non-compliance with the Article 4 requirements for authorization for a long time, and nothing did happen. Yeah. So I think, yeah, it's not so easy to give a good answer on that, because on the one hand we do have in comparison to wherever on the globe the best regulatory framework for protection against the risk of pesticides. I'm convinced of that if you look in the 11/07/2009. On the other hand, as I said, I don't feel so well protected, but yeah, everything has its limits.
Yeah, well, it's also the sign of progress and how things evolve. It takes time. We are not aware of the full consequences, and the resources are not endless, unfortunately. But we touched upon technology, information, knowledge sharing, and trade-offs that we sometimes need to do. And you also raised, I think that the research that you're doing, Helmut, is also very important to start to call the attention for things that have gone unnoticed. And I'm quite curious about what was the grade of that student that highlighted the levels of TFAs in bottled waters. Thank you, Vera.
Yeah, I think, thank you, Bárbara and Helmut. I fully agree. There are indeed like these keywords, that is technology, now AI, that we could also use in our advantage also to understand better the challenges and possible ways forward. But I think what I personally find very challenging is about these connections, in the sense that we do have pieces of information here and there, we do have pieces of regulation here and there, but putting all of us working together, it's very challenging. Even when I'm talking about transition, a lot of, in this case, farmers, they are aware of some experiences, some success stories they implement here and there, but sometimes we ask, so how come this is not done at a larger scale, like with more impactful, like what is happening if the knowledge is there, if data is there, if there are technology that is going faster and going cheaper, or to make it also more accessible, why is it not happening? Like sometimes it's, I'm sorry to put it a bit frustrating, it's like I'm not getting it, like what's happening, what's holding here? What are the bottlenecks? And I do think indeed is to make these bridges. Because if we tackle them, I think there are some cascade effects that could be also very beneficial for us once these bridges are salvaged. So we should not, in my perspective, not only look at MRLs and see if we as consumers are safe. That's crucial. I fully agree. Don't get me wrong, and great job there, in my opinion. But I also think that we need also to be mindful. Yeah, if the practices are not sustainable, how are our resources? Do we even have food? How is our food waste? So there are all systems that needs to be tackled so that sustainability comes across. So in my perception, it's mostly about bridges that brings a big challenge.
Thank you, Vera. And we finish on a very positive tone. Collaborations, it's
Yeah.
what we need. That's why we are all here to try to find solutions. Hopefully our paths will come across in a near future. I have to say it was a pleasure to have you here. Really enjoy hearing your presentations. To our participants that are still here, I already put here the forms where you can, just fill in very short quiz if you want to get your certificate. I'm sure Soraya is going to place the link here also in the chat if you're not all. So before I wish you all a very good Easter, just to remind you that we end these webinar cycles on the transition from pesticides to biopesticides, and we have already prepared a new one for you. We will talk about science communication. This time we will take a longer break because we have some bank holidays in Portugal in the meanwhile, but we'll be back on the 8th of May talking about ways to communicate science to different stakeholders. And of course, our basis is agronomy and agriculture. So this will be our focus. From my end, that's all. I give a warm thank you to our speakers, to our participants, and of course to my team that I could not go without. So many thanks also to Rita and Soraya for all your support. Wish you all a very good Easter, and we'll be back in May. Thank you.